Morning Year 12. Sufficient numbers of you have said that you struggled with the homework, so I'm going to go through the mark scheme now. It'll be quite brief, but hopefully you will see what's going on here. So question 1, 2-methylpropane, smaller standard molar entropy at 298K than butane. What's the best explanation? Well, if methylpropane had a lower boiling temperature, it would be more likely to be a gas, and therefore it would have more entropy. So it certainly isn't that one. Enthalpy change, well, entropy is really nothing to do with entropy, so it's not going to be doing that. So it's all about how the energy can be distributed. And if it's got a smaller standard molar entropy, that means there are fewer ways of distributing the energy than for butane. And therefore C is the obvious answer, and about 86% of you got that. Questions about enthalpy change and entropy changes. Which reaction has a negative value for dSsystem? So we're looking for something where obviously there's going to be a decrease in entropy. Usually that would be something like a gas being destroyed. So here we've got a gas turning into a solid, so that would be a large negative decrease in entropy. Here we're creating a gas, so that would be a positive change in entropy. Here we're creating a gas, so that would be a positive change in entropy. And here solid and solution and gas would be positive. So the only one which would have a negative change in entropy was that one, and that was got by 95% of you there. In terms of these, almost all of you realised you're making a gas, so that would be a positive. In fact, 100% of you realised that would be a positive change in entropy. For row 2, we've got a solid turning into ions. These ions here, aqueous, are obviously free to move. They've got more entropy, and 95% of you realise that would be an increase in entropy. But for this one, you're going from 4 gas moles or molecules to just 2. So you're losing gas, and therefore it's a negative change, which 98% of you were fine with. This question here, what is the expression for dStotal? Well, hopefully you know that dStotal equals dSsurroundings plus dSsystem, and dSsurroundings can be replaced by minus ΔH over T, so it's dSsystem minus ΔH over T d. 85% of you got that right, but a lot of you going for dSsurroundings. But no, the system is what you calculate in the method akin to Hess cycles. It's the surroundings where we can work out the energy from the enthalpy change divided by the temperature. Question 5 about entropy and free energy. Calculate the total entropy change for the thermal decomposition of calcium carbonate at 298 Kelvin. Well, that's fairly straightforward. dStotal is dSsystem minus ΔH over T, which we just saw, which is plus 160 minus 178,000 divided by 298, and that should give the answer of minus 437 joules per Kelvin per mole, minus 437.3, and that is what the vast majority of you got here. 78% of you got that correct answer. If you work just this bit out here, that's where the minus 597 comes from, to 3 significant figures. So minus 597 there, and minus 437 there for the entropy change of the surroundings, and then total. You can see some people putting units in here. Show that the reaction is feasible at 298K by calculating dStotal in joules per Kelvin per mole. Give your answer to an appropriate number if significant figures. That's here. Okay, So delta S system is products minus reactants, so it's 2 times 193 minus 192 plus 3 times 131, and that gives you minus 199 joules per Kelvin per mole. Entropy nice and easy because you don't have to worry about negative signs so much. But yeah, you can see that 76% of you getting that right. Quite a few people putting in units there. But yeah, it's products. There's 2 of the ammonias and there's 3 hydrogens. Don't forget to multiply the entropies by that. dSsurroundings, again, only 72% of you getting that right. Delta S surroundings is minus delta H over T, so that is minus 92,000 over 298, which equals plus 309 joules per Kelvin per mole. Few people, there you go, 0.309 there, so someone at least forgetting to convert that into joules, and therefore when you add those together, minus 199 and 309, delta S total is minus 199 plus 309, which equals plus 110 joules per Kelvin per mole. 63% of you getting that correct, but quite a range of strange answers here. No particularly prevalent one, but something going wrong with some very simple calculations there. You should have done these loads of times by now. So quite why only 63% of you got that answer, I don't know. Now, the original question, explain in terms of entropy why this reaction is not feasible at very high temperatures, was a free answer one. If we think about it, delta S total equals delta S system plus delta S surroundings, and the system has a negative entropy, so this is bad for spontaneous, but delta S surroundings is a positive number. There you go, and that is good. But as the temperature goes up, delta S surroundings gets smaller, less positive, until eventually the plus is smaller than the minus and the overall thing becomes negative. So which of those answers matches? At high temperatures, the entropy change of the surroundings becomes less positive. Absolutely. So remember, the temperature affects the entropy change of the surroundings far more than the entropy change of the system, because the surroundings is minus delta H over T. Bigger T, smaller value for that term. 67% of you getting that right. This was distressing, okay? This is a standard GCSE question, guys. This is a really standard GCSE question. A reacting mass calculation. I've got my year 10s doing this, okay? And that is kids who have no intention to do chemistry whatsoever past this. And if they can do it, I don't understand why only 56% of you got this right. Not good. Right, 398 kilograms of sulfur hexafluoride. Moles is mass, 398,000, divided by MR, 146.1, which equals 2,724 moles of sulfur hexafluoride. Now it says the mass of lithium that you need. Well, it's a 1:8 ratio. So therefore, moles of lithium equals 2724 times 8, which equals 21,793, and therefore the mass is moles times MR, which equals 21,793 times 6.9, which equals 150. Lost my pen. 150,000 grams or 150 kilograms. The biggest error, I presume, is this one here, 150.4, but it did say give your answer to an appropriate number of significant figures, and the actual question wants you to realise that given that this is given to 3 significant figures, you cannot give your answer to any more than 3 significant figures, so 150 kilos. But 56% of you getting that right, that is just distressing. The table gives the standard molar entropies, calculate the total entropy change delta S total for the reaction, include units. Right, well, delta S system is 6 lithium fluoride, 6 times 35.6, plus just one of those, 63, minus 8 lithiums, 8 times 29.1, plus 292. And that equals minus 248 joules per Kelvin per mole. Delta S surroundings is minus delta H over T, which equals minus 2,934,000 divided by 298, which equals, as it says down here, plus 9850 joules per Kelvin per mole. And therefore dStotal is 9850 minus 248, which equals 9600 to 3 significant figures. Provided you gave it to 3 significant figures, it's 9600. 9598, at least one person just forgot to round that to 3 sig figs there. But 47% of you getting that right, that's not particularly good, is it, right? And having a look at this, delta S system, 70% of you calculating that right, but delta S surroundings, there's no reason actually that should have been only 60% of you getting that right. Now this is something you haven't covered. The reaction between sulfur hexafluoride and lithium is started using a fuse. Justify the need for a fuse in view of your answer to part B. And I wanted to see whether you guys could work the answer out to this without me having to tell it to you. And the answer is basically that although if we have free energy here, G, so no, not the normal H, but free energy G, and this is the products and the reactants and products, although it is favourable, thermodynamically favourable, in other words, although entropy, good for entropy, there is a huge activation energy barrier. And therefore you need a lot of energy to start the reaction off. So although the reaction is spontaneous, there's a very high activation energy barrier. About 70% of you getting that, which is great. Fuse raising the temperature so the reaction becomes spontaneous was a nice try there. But actually that wouldn't work, because if you have a look at this, the entropy change of the system is negative and the entropy change of the surroundings is positive. So as the temperature goes up, this number gets smaller. So it is less likely at high temperatures. Just like the previous question, okay? So it's not that the fuse is making it spontaneous, actually the hotter the temperature, the less likely this reaction is, because it's exothermic. Again, tie this idea to Le Chatelier. Okay, question 8. So you got the original question here where you had to look up the values from the data booklet and then use them. You didn't have to, so it's surprising that 25% of you got this wrong, that delta S system is H2O 69.9 minus H2 131 plus a half of O2, half times 205, and that hopefully gives you an answer of minus 164 joules per Kelvin per mole, and 75% of you got that. The standard enthalpy change for combustion of hydrogen, minus 285.8. Use this value to calculate the enthalpy change of the surroundings. Give your answer to 3 sig figs, include a sign and units. So delta S surroundings is minus 285,800, because I've converted that into joules, over 298, which equals plus 959 joules per Kelvin per mole. And again, 65% of you, but what are the rest of you doing? I mean, honestly, look at all these answers. And for something that is so straightforward, minus delta H over T, I do not understand why over a third of you are getting that wrong. I mean, some people, yeah, have just put in answers. Some people have forgotten to convert from kilojoules to joules. But some people, what everyone else is doing, I'm not quite sure. So therefore, the total entropy change for that delta S universe or total is plus 959 minus 164, which equals plus 795 joules per Kelvin per mole. And again, they're asking you in the question, the real question, for the sign and units. By considering both the thermodynamic stability and kinetic inertness of a mixture of hydrogen and oxygen, explain why hydrogen does not react with oxygen unless ignited. Well, again, just like the previous example, if we have a free energy diagram, this is G, free energy, which you will learn about, or you have learned about in lesson 3, not H, but G, reactants, products, it is thermodynamically unstable. In other words, it wants to fall apart into products. Thermodynamics say it should fall apart into products because the products have higher entropy, lower free energy. But what's stopping it is this very high activation energy, so that means it is kinetically stable. So mixture is thermodynamically unstable, a positive entropy change, yes, upon the reaction. So it is favourable to fall apart into products. But the high activation energy prevents it. 40% of you got that. It was the best answer, or the highest numbered answer, but just behind that, people got it was kinetically stable, but it's thermodynamically unstable because there's a positive entropy change. And finally, we get to this question about adipic acid. Now, the first part, use the data booklet to complete the table below. This bit was done for you. Use data from the table to calculate the standard enthalpy change when adipic acid is formed from buta-1,3-diene, carbon monoxide and water. Shouldn't have been under half of you getting this right, because this is a standard enthalpy change question. So delta RH is the enthalpy change of formation of the products minus the enthalpy change of formation of the reactants. So it should just have been minus 994.3 minus plus 109.9 minus 2 times 110.5 minus 2 times 285.8, and that should have given you minus 311.6 kilojoules per mole. That's 2 times 285.8, okay. 311.6, less than half of you getting that right, and really, given that that was topic 8 stuff that you should have revised for your end of year exam, there's no reason under half of you are getting that correct. Calculate the standard entropy change, exactly the same. Entropy change of this reaction is the entropy change of the, or the entropy I should say, of the products minus the entropy of the reactants, which equals 250.0 minus 278.7 plus 2 times 197.6 plus 2 times 69.9. That should give you, to 3 significant figures, minus 564 joules per Kelvin per mole. Calculate delta S surroundings and delta S total. Delta S surroundings is minus delta H, 311,600, converting that into joules, over 298, which equals plus 1050 joules per Kelvin per mole, to 3 significant figures. 1050. A few people forgetting to give it to 3 sig figs, a few rounding errors there. And finally, therefore, delta S total equals plus 1050, although the not rounded version, minus 564, which equals plus 482 joules per Kelvin per mole, or if you use the rounded version, plus 486 joules per Kelvin per mole. And this is why there were 2 common answers here, 482 and 486 there. It was suggested that decreasing the temperature of the reaction to less than 298 K would produce a greater yield. Explain in terms of the effect whether this would be the case. Well, delta S system would be unaffected. Delta S surroundings, okay, if the temperature got lower, that would get more positive. So it's a positive number, okay, up here. It's a positive number, and if we get lower temperature, that will be an even more positive number. And therefore, delta S total gets more positive. And that would lead to a greater yield. Finally, infrared spectroscopy can be used to follow the progress of reactions. During the reaction, suggest one peak that diminishes and one peak which appears here. So we've basically got an alkene here forming this. So what we're going to lose? Well, we're going to lose the alkene, and that is the peak 1669 to 1645. If some of you were thinking about CO, carbon monoxide unfortunately is a triple bond. So that is not the CO peak. It's triple bond. So that's why that was a red herring there. So that did not diminish. And you've got 2 types of OH peak appearing here. you've got one at 375 to 3200 and one at 3300 to 2500, and the one associated with the carboxylic acid is the one that appears at 3300 to 2500. That's in your data book, so you would be able to tell that. And finally, adipic acid is used as an additive in some fruit jelly. So just what effect the adipic acid will have on the flavour of the jelly. And it specifically says not, in the mark scheme, not more acidic. It is more sour. That's what they need you to say, that acids give a sour flavour. Yes, they would be more acidic, but that was not what it asked. It asked you for the flavour.